This is the avascular tumor simulation, very important simulation to understand how fields interact with tissue, okay? And if you are not here for cellular biology, maybe temperature field is important for you. And in this case, you would like to learn from this lecture, okay? So remember that the workshop is live streamed, recorded, and distributed. My name is Pedro Castel, in case you don't know me yet, and I am from Indiana University. Actually, I'm from Brazil, and I'm studying in Indiana University. So in biology, experiments show that the tumor is composed by layers. So the outer layer is the layer where cells can proliferate because they have easier access to nutrients. And the inner layers are, for example, quiescent cells, where the cells don't have enough access to nutrients to proliferate. So they enter a state of low maintenance. And the most inner layer, in the center of the tumor, there is the necrotic zone, where cells don't receive enough nutrients to survive, and they die. They undergo apoptosis. So some basic characteristics of tumor is that it grows, okay? The tumor spheroid grows, and this is a microscope. This is microscope pictures of an experiment. And some questions we can ask, for example, how it differs from in vitro and in vivo. It's definitely different because in vivo, it interacts with the environment in another way. And in vitro, you can control much better the outside of the tumor. So depending on the access to nutrients and to oxygen, you can have different growth rates. And you can, for example, achieve equilibrium, dynamic equilibrium in the tumor, where it grows at the same pace at the necrotic cells die. In this case, you could ask, for example, what is this size depending on the fields I am providing to the tumor, at which rate I, for example, give the tumor nutrients from outside, and what is the outcome of this specific rate in terms of growth, okay? Tumors absorb nutrients, and if you were here in the last few lectures, you saw this graph. This is an experimental graph measuring the concentration of oxygen as you walk inside the tumor. So I don't know if it happens, but if someone is walking inside the tumor and measuring the concentration of oxygen, this person would measure this curve here, an exponential decay in space, where you can, for example, measure the typical diffusion length, which is how far into the tumor the field can penetrate. In this case, the field is oxygen concentration, but it could be glucose concentration. And you could also do the other way around. Cells dying release toxins, and these toxins diffuse from inside the tumor to outside the tumor. Okay, so there are many diffusive fields you can model in this particular system. Okay, the nutrient field, as I said, it has this exponential profile both ways, and it reaches a minimum inside the tumor, and cells will differentiate depending on the concentration of these fields. For example, depending on how much access you have to oxygen, you can proliferate, or how much access you have to nutrient, you can proliferate. If you have lower concentration, you may only be able to survive and not doing anything else. In this case, you will be called quiescent, which is my case in my personal life now, just surviving. And necrotic, you don't have enough access to nutrients and oxygen, so you just die, okay? So we would like to model these 3 cell types: the proliferating cell type, the quiescent cell type, and the necrotic cell type. And we also want to switch states based on the concentration of the field inside the cell. So for example, you start with a bunch of proliferating cells, and as they grow, nutrient decays inside the tumor. And as it decays, cells inside start becoming quiescent. So you change cell type and switch them to quiescent. And if for some reason a quiescent cell start acquiring more nutrients, well, then you switch back to proliferating, okay? So proliferating to quiescent is not a irreversible switch. You can switch both from proliferating to quiescent and quiescent to proliferating. On the other hand, quiescent to necrotic is irreversible. So you cannot revive a cell. In this simulation specifically, you cannot revive a cell, but if you are interested in magic, you may want to build another model. We also want to build the boundaries, to model the boundaries. So we have many options. For example, do we set a constant concentration value at the boundaries? Do we set a constant influx of nutrients from the boundaries? Do we set periodic boundary conditions with, for example, the medium secreting nutrients? Could be the case, right? Could be that the medium is producing nutrients for the tumor, and could also be the case that we will model here, which is the medium fix the field at a constant value. In this case, we are supposing that nutrient replenishment in the medium is too fast in comparison with tumor growth. So although the simulation is very fast, you see the tumor growing and shrinking, growing and shrinking, the hypothesis, the assumption here is that the medium replenish nutrients much faster than the tumor grows. So this is the boundary condition we are going to model here. Medium holds field at a constant value. Quiescent, okay. Quiescent cells. I just got a pronunciation correction here from Juliana. So our simulation starts with a quick exercise for you to try. So I'm not coding here for you. You have to follow the steps in the slide, okay? So first of all, create a new simulation, put the name, for example, Pedro is a nice guy, a name that really makes sense, okay, for the sake of this exercise, and set a lattice with periodic boundaries, 256 by 256, use blob initializer and set a copy range to 2. That's the first thing you're going to do in your POTS configuration. Then in the cell types, you are going to define prolif, quies, and necro. And for the chemical fields, a nutr field. So it's a 2D simulation, shall I? It's a 2D simulation, so Z doesn't matter. So leave it as no flux. Actually, I never tried. It doesn't matter. It really doesn't matter. It will lead to same results. Define your field, neutral, and choosing diffusion over Fe. And then the properties, contact, secretion, mitosis, and volume local flex. So why volume local flex instead of volume flex? Good question from my mind. So volume local flex allows you to set specific volume per cell, while volume flex only allows you to set volume for each type. So in this case, we want some specific cells to grow. So we want to change their volume specifically for each cell, change their volume. So volume local flex allows this and volume flex doesn't. Oh, I didn't put growth. Yes, well observed. So for some reason, I forgot growth. Nice, thank you. Growth plugin is not needed here. No, it's needed. It's growth here. Can you see it? Growth here in the slide. Somehow you missed it. I don't know what you're talking about. Yeah. And in the secretion tab, set medium to secrete the field neutral at constant concentration 100. So why 100? Because we want to relate, for example, 100%, etc. Okay, good. I will put my slide to the side. I will leave it on the screen, and I will do it step by step now, just to make sure I am on the same page as you guys. So yes, some angiogenesis simulations here for a lecture later today, which is very important. So new project, Pedro just woke up. Okay, 200 periodic, copy range 2, it doesn't matter actually, blob. Next. Prolif, yes, and necro. Next. Neutral, diffusion solver, okay, next. Yes, Shalai, yes. But you can leave it in blank, yes, and set in the XML as we did yesterday. Contact, secretion, growth, and volume flex. Contact, secretion, growth, mitosis, and volume flex, yeah. Next, secretion plugin, medium, to secrete nutrient at a constant concentration of 100. Or you can set it in the XML, which I'm about to show. add entry, finish. So if you are setting the XML, let me go to the XML. If you go to your XML and you implemented a secretion in the wizard, you should see this constant concentration, type medium, 100. So if you didn't get anything like this, you can, yes, you can do stuff. Yes, probably in the steppables, it's better. So uniform is the constant rate, I think. Yes, constant rate is the uniform. If you didn't get anything, you can leave the secretion window blank and go to the steppables and implement secretion here. For example, not here. Yes, inside one of these. No, yes, outside. Interesting. No, do it in the XML. Let's simplify the problem. Do it in the XML. So inside the plugin secretion, you should have this syntax here. I can give it to you in the chat exactly how it is.
You DM'd me, Pedro, instead of putting internal chat.
Ah, okay. Thank you. Similar to constant value boundary condition except everywhere. Yes, Sharon. Yes. Your second question about secretes just the amount to keep the total environment concentration constant. I would rephrase that. I would say that it's not exactly a secretion. Although we are modeling secretion using this, it's not exactly secretion per se. So it's constant concentration in medium, everywhere in medium. Not everywhere in the simulation because you would also be talking about cells. But in all medium, constant concentration of 100. I have to make sure you guys are with me here. So I'll bother you once again with the poll. Okay, let's move on. Now in your XML, set the global diffusion constant to 10, set the global decay constant to 0.01. Notice that the global decay constant will not affect the medium because medium is holding the concentration constant. So it will only affect the cells. So set global decay constant 0.01. Comment out the lines referring to diffusions and decays for specific cells. set the initial concentration of the field to 100. So there is that commented line saying initial concentration, uncomment this line and write 100 between the brackets. Then comment out secretion lines inside the diffusion steppables, since we are using in the secretion plugin already. And set boundaries to periodic. In the blob initializer, width to 8. And only prolif cells. So we are going to start with only prolif cells. No necrotic, no quiescent. But you could leave some necrotic, some quiescent. It doesn't make sense. It doesn't make a difference. Okay. You can leave the 3. It doesn't matter. Yes, Sharon, that's a better interpretation of the simulation. There is some valve that automatically adjusts medium concentration to 100. So Melanie, in your diffusion steppables, I will show you in the code here. So take a look here. This initial concentration expression, this line here, around 77. You uncomment it, pressing Control bar, and type 100 here inside 100 and save like this. Yes, Melanie, yes. No, tamanho, initial initial concentration is the initial concentration. And is the concentration everywhere in all lattice, not only in medium, in all lattice, in the cells either. So diff and decay for specific cells, here where you find diffusion coefficient and decay coefficient for cell type, prolif, quiescent, necroprolif, these are the specific cells, okay? So Schley, it goes inside the secretion plugin. Here. I will give you 60 seconds. In the diffusion solver, you must comment as well. You must comment. In the diffusion solver, you comment the secretion. these lines here. You must comment them. Okay, now I will do myself here. Do it myself. So set global diffusion constant 10. So I come here 10.0. Global decay constant 0.01. Initial concentration 100. Initial concentration 100. Okay. Then comment out secretion lines inside the diffusion steppable. So where are, no, comment out diffusion and decays for specific cells. So all these lines here are diffusions and decays for specific cells. Control bar. Commented them all. Now comment out secretion lines inside the diffusion steppable. So these 3 lines here, control bar. Now, periodic conditions here in boundary. Periodic conditions. So comment the others and uncomment periodic. And now with 8. And only prolif cells. That's it. Okay. Okay, let's move on then. In your steppables, do that in the slide. Do that. Read the slide and do it. So change the target volume to 64, lambda volume to 8. Then comment out the 4 lines in the bottom of the simulation. They are switching cell types when the cell divides, which is something that we don't want. So get rid of these 4 lines. I will do it myself. So slide to the side. I am on my steppables file, the Python file. Here in the constraint initializer for cell in cell list. So this is looping over all cells and initializing their volumes and lambda volumes because this is a start function. So this is an initialization. 64 here, 8 here. Save. Now in the mitosis down there, you just get rid of these 4 lines. So I will comment them out. So this preposition is important. Otherwise, it could mean commenting. Good English lessons from Hayden yesterday. Oh, my volume threshold. Yes, thank you. Thank you. I was just trying to see if you could notice that I forgot the volume threshold. Okay, next. The most difficult one is to run the simulation. So how do I do this? I have to go to here, project, show, project, open in player. So you should get the same result as in the video. So should I got a bug? Let's see if I got it as well. So your computer cell crashed, basically. There's a bug somewhere. Could be in the XML. Bugs in the XML crashed computer cell immediately. So typos, etc. Still not launched CC3D. Yes, Julio, so that's a problem. Set your Z dimension to no flux instead of periodic. Yes. Thank you for giving us that error. Line, no. And while you fix your issues, I fix mine here because my CC3D doesn't open for some reason. I think I have to reload CompuCell. You have to be very careful with typos in XML. Where is my simulation? I will reset my to edit. Okay. This is the simulation. I'll go to the XML as Fatime asked and open in player. Okay. Yeah, so mine is working. It's extremely slow for some reason, but it's working. Notice that I only did things said in the slide, okay? So the only potential difference is that I didn't commit any errors in terms of typos. And why is it so slow? Let's see if it has a. Why is it so slow? I don't know. I don't know. Oh, could be Zoom. Yes. Zoom could be messing up my, I don't know, RAM. Oh my God, that's slow. But yeah, I have to change colors here. So any other color works. Okay, red. Good. Wow, that's slow. So it should grow like this. Bah, really fast. In like 5 seconds, you cover the entire medium with cells. So if you want to reset to if you want to reset to no flux, just delete the periodic setting for the Z dimension, okay? So to get rid of the Z periodic boundary condition, just go to your XML in your POTS specification. You select the line and delete like this. Select, delete, select, delete. For your Z dimension, okay? So let's replicate your bug. So if there is a Z here, it will give me a bug. Let's run it again. Yeah. So exception during initialization parsing, lattice Z dimension must be greater than 1 for periodic boundary conditions. Location, yeah. So you'll come here, select, delete, save, and it should work fine. That's slow. All right. Yes. So if you want to better visualize your field, go to Tools, Configuration, and for this particular simulation, you can set from 0 to 100, both fixed. Okay. And there we go. From 0 to 100 fixed. Red is 100, blue is 0. So again, Tools, Configuration, Fields tab, and fix the range, set 0 to 100. Okay, I will move on. Now we have to switch types, right? So we have 3 cell types, and based on the field intensity, we want to switch types. So for example, if a proliferating cell reaches a first threshold, it becomes a quiescent cell. If a quiescent cell reaches the same threshold, it becomes a proliferating cell. And if it reaches a third threshold, it becomes a necrotic cell. Actually, we just need two thresholds. The threshold at which occurs the switching between proliferating to quiescent, and the threshold where you only get the switch between quiescent to dead, okay? To necrotic. So let's implement this. How do we do this? So the idea is go to your steppables, and in the growth steppables, you must loop over proliferating cells and quiescent cells separately. Then in the proliferating loop, you set a condition that if the concentration of the field in the cell center of mass is lower than a certain amount, it becomes, you change the type to quiescent. If not, if it's still above, you allow the cell to grow. Okay, so growth must be set only for proliferating cells. And in the quiescent loop, you set an if statement testing if the field is above this quantity, the concentration. If it's above that concentration, you switch back to proliferating cell. If it's lower than another threshold, you switch to necrotic and update the cell volume, the cell target volume to 0, so the cell disappears. Okay? So first things first, go to your steppables and substitute the previous loop over all cells for 2 separate loops, one over prolif cells and another for quiesce cells. You can take the syntax in the menu Python visit all cells of given type. I will give you a minute to do this. I'm about to reach this point, shall I? But if you want to do this, the syntax is already there. If you take a look at your simulation, the syntax is already there. You have concentration at, something like that, concentration at, COM, something like that, equals field, open parentheses, square brackets, center of mass X, center of mass Y, center of mass Z. And then you parse it into your if statement. Okay, I'll do it now. You had enough time. So basically what I want you to do is go to your steppables, go to your growth, delete this guy over here, substituting it for a Python visit all cells of given type. But we need one for proliferating cells and another one for quiescent cells. Let me just delete the rubbish. So here, instead of this rubbish inside the parentheses, you put another rubbish, prolif and quiesce. These are our 2 for loops over cells of a given type. The first one over prolif cells, the other one over quiesce cells. Make sure you are on the same step as me. Yes, capitalized letters. Don't type like this, prolif. Wrong. Prolif. Right. Okay, so now you should get something like this, which you didn't show, sorry. Next slide. Before the loops, get the field object of the field nurture. So before the loops, outside the loops, get the field object, which is field equal self dot field dot nurture, like this. So here is the name of the field. So I set it to I set it to nurture. So I write nurture here. So if you set it to Pedro Handsome, you have to write Pedro Handsome here. Which variables, Julio? So field is a field object. It's this field nurture. So it carries X, Y, and Z components. So if you do this value equal field, this is not for you, okay, guys? Don't copy me. Like 50, 50, 0. No capitalization for the field name. Capitalization is only for cell types. Don't ask me why. So if you do this, you are just getting the field value at the position 50, 50, 0. X equals 50, Y equals 50, 0 for Z. So for example, in your simulation, Julio, if you want to know what is the temperature in your solid at some point, you can just take the temperature and measure it in a certain position. After you do this, take your concentration measurement. There is a syntax here. Measure the concentration. So this is basically what we are doing now, what I was teaching Julio. So basically you use, so no parentheses, I'm sorry for that. So field is a matrix. So you can just type the cell center of mass in the X, Y, and Z components, and how you access the center of mass. Just type cell dot X lowercase, COM uppercase. I can copy and paste this line for you guys in the chat. So Julio, if you want to know the temperature in your cell, in your simulation, you will basically use this syntax over there. Field, then vector, X, Y, and Z components. And do this in both lines, okay? So get the concentration in both lines for each cell type. I will show my code in full screen here real quick so you can see everything. Can just copy this line over here that you received commented and paste inside the cell type loops. Slap in your face again. Okay, we're good. So far, we have 50 people completing the exercise, although we only have 34 in the Zoom. So let's keep going. Next step. Yeah, so now we want to set up the thresholds. So if concentration is lower than a certain amount, switch proliferating to quiesce. If it's still proliferating, make it grow. So this is the line here, target volume plus equals 0.5. In the case of quiesce, if concentration is above the same threshold, switch to prolif again. If concentration is lower than 40, another threshold, change type to necro and update target volume to 0. I will do these changes on myself. So very slowly here. First, test if the concentration at center of mass is less than 70. If yes, change cell type to quiesce. If not, else it is still a prolif cell, then make it grow. So target volume plus equals 0.5. Now do the same thing to quiesce. Test the concentration. If the concentration is above 70, switch the type back to prolif. If, on the other hand, concentration is lower than 40, cell type changes to necrotic and the target volume goes to 0. So the cell dies. Yes, Lambros, yes. So you can correct this, doing, for example, cell target volume plus equals 0.5, but there is no need to do this. There's really no need to do this. Please type in the chat your problem. Otherwise, I will move on. Okay, so I think that's it. Actually, this is the last slide. Let me just, yeah, this is the last slide. So you can run your simulation and see how beautiful it is. So what is happening here? The field diffuses inside the tumor. The tumor makes the field decay. So this is modeling absorption. And it's modeling uptake of the nutrient. And as the tumor grows, the inner cells start to change type to quiescent cells and to necrotic cells. So the quiescent cells in the middle, they do not grow, they do not divide. And I got an error. No attribute necrotic. Where is it? No, because I don't have necrotic, my cell, my type is called necro, not necrotic. My mistake. It's necro, yes, necro. Yeah, so now it will work. Okay, it grows, nutrient depletes inside the tumor. It has a typical penetration length inside the tumor, and the cells inside change type to quiescent, and eventually they will change type to necrotic. And the necrotic cells have volume 0, target volume 0. So you can see a necrotic cell here, many necrotic cells, and the tumor starts collapsing because the inner cells die, the tumor shrinks. And as the tumor gets access to new nutrients, it starts growing again. So it grows and shrinks in cycles. Okay. There is another important phenomenon happening here, which is as the tumor grows and shrinks, it always shrinks asymmetrically. So it will leave a bunch of cells here, a bunch of cells there, etc. And it starts spreading throughout space, even though it does not have migration. So because of this asymmetric shrinking of the tumor, which is a feature of CompuCell, so CompuCell is stochastic, you would not be able to model this using, for example, continuous models. So you can already see that this irregularity in the tumor form here, this irregularity will eventually lead to tumor spread across space. So we can just wait and see it happening. So you can play a lot with this simulation, changing thresholds, changing growth rate, changing the boundary conditions. You can change the boundary conditions, making for example, the medium secrete at a constant rate instead of holding a constant value, or you can make the boundaries secrete, or you can make the boundaries hold a constant value and see what could be, for example, the maximum size of this tumor, okay? Depending on the boundary conditions. Yes, mine is too slow for some reason, probably Zoom. This is Giuliano's hypothesis. So here's something like, no, our secretion is not consuming. Our consumption is the decay in the diffusion steppables, Schley. Our consumption is decay. If you take a look at our decay, global decay constant, 0.03, this is our consumption. The 100 positive value that we set in the secretion, this is the value that the medium holds constant. So the medium is the provider of nutrients to the tumor. This is important. Yes. Okay. You got it. So see how it spreads, right? the tumor spreads, and it can grow to a bigger size because as it spreads irregularly, it acquires more surface contact with medium. And as the medium is the provider of nutrient, when you have more contact, more surface of contact with medium, it allows the tumor to grow more and to grow faster. All right. But there is a problem with this model, which is we are not accounting for the exact value that the cell is uptaking. For example, proliferating cells take up more nutrients than quiescent cells, and necrotic cells do not take up any nutrient at all. So in order to take this into account to our model, we would need to implement the uptake as instead of the decay as we done. And the uptake would be dependent on the cell type and dependent on, for example, how much nutrient the cell has access to. So for example, if it's a proliferating cell, the proliferating cell will uptake, let's say, one amount of material per second. If it is a quiescent cell, it will take up half of this amount, for example. And if it's a necrotic cell, it will take 0. So probably the right way to proceed here would be to take a look at a paper, at an experimental study, and see what the measurements are. And then implement these measurements in your tumor and see if your results in the simulation match the results in the experiments. So I hope everyone got a similar result as mine. I will slap your face once again with the poll. I'm happy to see that you guys could complete the exercise. This was not a follow along exercise. So I put a slide with instructions, so you have to read the instructions and do it yourself. There is a downside to it, we take longer, but the good part is that you learn much more because you have to pay attention to what you are doing and think critically about what you are doing. And then these important questions that I looked at in the chat: why you're doing this, why are you doing that, why are you using decay, where is our absorption, where is this, where is that? So all these important questions start popping into your minds. So this is the purpose of this other model of teaching. Okay, I hope you liked this simulation. There is plenty of stuff you can do in the simulation to play with it. And you can even turn this simulation into a hackathon project. So for example, you could implement uptake, and you could also implement growth proportional to the amount of material taken up by the proliferating cells. So all these changes would make a interesting hackathon project. And we can even publish this project as a demo in, for example, an educational journal. I hope you liked it. So if you want to follow the next exercises, there is, for example, nutrient-based growth. So make the growth of proliferating cells proportional to the amount taken up by them. If you're interested in reading about cancer, how it works, I highly recommend the Hanahan Hallmarks of Cancer, where he covers the main important features of cancer that it uses to survive. tumor. It is resistant to cell death, for example. It mutates. It induces vasculature and many other features. So you can start from that simulation and implement all these features or the ones you are most interested in and come up with a good hackathon project if you want.
And jump in here for just a second, Pedro, since we're nearing the end of this module. I'm going to run the module experience poll, people to be filling out.
Fill the questionnaire. This is very important for us. If you didn't like the format of the exercise, please type it for us. Leave a comment about it. Suggestion, criticisms, very important. So we can build better lectures for example, next week and for future workshops. Please fill out the questionnaire. It's important for us. This is our trade. We teach you how to use CompuCell, and you teach us how to teach CompuCell. That's our trade. So thank you very much for participating. Please fill out the questionnaire. And I will see you again later today on the angiogenesis exercise, which is a very fun one, much funnier than a vascular tumor. In order to build the angiogenesis, you have to understand chemotaxis and forces over cells in CompuCell. So please pay attention to the next two lectures, one about forces over cells, the other about chemotaxis, and this will be enough for us to build the angiogenesis in the end of the day. If you want to take a look at the chemokinesis model, you can access it in the demo codes in the students' materials. So feel free to download and run in your local machine or NanoHub.